Hi, Michael. And Rob?
Hey, David, how are you?
Good, good. How are you?
I'm doing well. Let me turn on my camera. There I am.
Yeah, haven't seen you for a while. So
No, it's been a little bit. Yes.
everything good?
Yes, everything's just fine. Yes, good to see you.
Good to see you. So you can hear me okay?
Oh, I hear you just fine. I have to retrain my Bluetooth settings here, but yes, I hear you just fine.
I see, I see. Okay. So I'm not going to use, I will just use the built-in microphone from my Mac, but I think it works well, right?
Yeah, it works just fine, actually.
Okay.
Yeah, no, it's
All right. So I guess we're starting a few minutes. I just joined a little earlier. Do you want me to test my screen sharing?
Oh, you can. I mean, I'm sure it'll work just fine.
Oh, yeah. Okay. It looks
it
like
seems to be, you seem to be coming through just fine. So there's no
yeah.
latency in the connection. So
Right.
anyway, but yeah, I finished reading the paper you shared with me. That was a very good paper.
Oh, thank you. Yeah, we actually have a lot of papers on this topic. So I will, basically today I will give an overview, and towards the end, I also have the reference. Right? So
Okay. No, it looks like very good work that you and your team have done. And I think it looks like a lot of novel ideas that have been applied to the problem. So
right, thanks. Yeah, my students are awesome. Oh, by the way, one of my students, Mingjie Liu, he also joined, just in case, right? If folks are interested.
oh, that's fine. That's
Some
fine.
kind of demo, but I will do some video demo, right? But
Okay.
if some of you guys are interested in some real demo, right? So we can show. But I guess it's a scripting, right? Oh, hi Minjie.
There is, and I see the tower behind him.
Yeah. Oh, this is Rob Mans. He's a general manager of Chip Alliance, an old friend of mine.
Hi, Rob. Hi.
How are you? Nice to meet you.
Nice to meet you.
Yes, I've been to UT a number of times, and I used to live in Austin actually too. Now I'm in the Bay Area.
Yeah. Actually, Rob had a big team in Oracle, right? I think when
yes, that's true.
In Oracle, right? So that's why he traveled here pretty often, and yeah, good old days.
And I see Michelle Loudis. I invited Michelle to join. Michelle used to work with me at Sun and Oracle, and we first met at Synopsys many years back. I don't know if you can hear us, Michelle. It says you're connecting to audio. Maybe it's not working right.
Oh.
Anyway, but yeah. Yeah, we should have a number of people joining us this morning. So.
Oh yeah, I think usually people may join 1 or 2 minutes late, right? So.
Yes, that's.
Yeah. And everything is recorded, right? So.
It's recording right now, in fact. Yes.
Yeah. Okay.
Which is good, as with the different time zones that we all have to work with. That helps.
Mm-hmm.
Yeah, I have a call today actually at 5 o'clock West Coast time with some folks in Shanghai about a FPGA project.
5 a.m.?
No, 5 p.m.
Okay, I see.
But actually, I am awake at 5 a.m.
I know, you are an early bird, right?
I am an early bird, yes, that's right. You recall well.
Yeah.
Oh, we have a number. Okay, we have a number of folks on the line.
Yeah. I think people are gradually joining, right?
Yes.
So we can wait a couple of minutes.
Yeah, we can wait a couple of minutes and we'll start.
So Chip Alliance does both analog and digital and analog, right?
Yes, that's correct. Right. Yeah, no, we have a number of different interest areas, aside from different implementations, or whether it be cores or architecture, if you will, for different accelerators or different interconnect type of protocol or cache coherency. We also do work in electronic design. And that's both digital and analog. And analog is a huge interest area, and as you well know, is a large challenge for design teams.
Okay, that will be great. How about FPGA? There's recently an open FPGA thing, right? Started
Right.
with, Utah, right?
That's right. Yes, I have been chatting with them actually.
I see.
And yeah, we are trying to get some work on it. Andrew just joined too. So why don't we go and get started? It's a minute past the hour. I think we've got enough folks, and people will trickle in as time comes along. So I want to welcome everybody to our meeting here today, and it gives me great pleasure to introduce Professor David Pan from UT Austin, and he's going to describe some of the work that he and his team have been championing in the analog space with Magical. And so I appreciate it. So David, why don't you go ahead and take it away?
Okay, thanks, Rob. Let me share my screen. Can you see my screen?
Yes.
All right, into the full screen mode. Thank you. Okay, all right. So thanks, Rob, for the kind of introduction and invitation. So I think since this is a relatively small audience, and please feel free to ask questions if you feel really there's something which you need a clarification instead of waiting until the very end. But of course, I can also exercise those questions and answers at the end, right? But feel free to ask questions in the middle. I might not check the chat box, right? But I guess just unmute your microphone and ask. Right? I will basically introduce a Magical open source automated analog IC layout systems, leverage human and machine intelligence. This is a project that I'm leading at UT Austin for analog IC layout. I'll give a little bit of background. I'm sure probably you have heard about that, but anyway, here is my outline. I will give a brief introduction, and then I'll talk about some overview of Magical, and then I'll describe the different Magical components, and then show some Magical results, and then conclude. So as we all know, right? So AI and all this, is a big booming, right? So there's the ABC behind the algorithms, the big data, and the chips, right? Which is really the hardware. That's where we are mostly working on, right? Whether it's analog circuits, digital circuits, or dedicated to AI accelerators. So, but the chip design and manufacturing has a lot of challenges, right? In terms of power, performance, area, manufacturability, yield, and so on and so forth. And not the least, the design cost, right? Really, also kind of follows the Moore's law. From older technology to more advanced technology, the design cost, the NRE cost really increased significantly. So that's why 2.5 years ago, DARPA started this ERI initiative, Electronics Resurgence Initiative. And under that, there's the IDEO and the POSH program, which basically, I think DARPA's vision and a grand challenge to the research community is how we can have a silicon compiler 2.0 that can have no human in the loop, 24 hours turnaround time. It funds many projects, I think, including Professor Andrew Kahn's Open Road. Thanks. I think I see Andrew in the audience. And meanwhile, there are also other open source projects for analog and FPGA and so on and so forth. Right. So, so among all these, of course, my work for this project is on the analog IC layout aspect. I do have a lot of work on the digital IC, but in this project, I'm mostly working on analog IC. Analog IC, although it doesn't have like millions of transistors or tens of millions, right? When you talk about digital, right, it's a huge design scale. However, analog design is very complicated. And in the sense that right now, mostly still treated as like art and heavily manually designed. But although they are like for the entire SoC, they may not be a very big components, but in terms of design effort, is huge. And also analog is becoming more and more important, with all this, 5G and medical, IoT, etc. You always have to communicate to the outside world, and the real world is mostly analog, right? So that's why we are trying to kind of really closing the design and design automation loop for the analog IC design, in particular layout aspect, physical design. Any question? Okay. Yeah, and Magical is a project that, as I mentioned, right, we try to develop a fully automatic analog layout systems. And we have already published a bunch of papers on this, and we have also open sourced Magical 1.0. And so actually, before even we started the DARPA project, we have had some NSF effort, actually 2 NSF efforts, including one which is ongoing for this. That's also helped us to build the groundwork for this. So in general, here's the overall framework of the Magical. So as you can see, the input is a netlist, which can be described as a SPICE netlist or spectral netlist with all kinds of PDK design rules. And the output is a GDS2 layout, which then you can do all kinds of validation, evaluation. So the big chunk of the Magical, we have there are 4 components. One is for device generation. There's not too much like intellectual novelties here. The reason we do this is to make it open source. You can definitely use Cadence, Virtuoso, etc. to do that. But we also have a kind of open source version for this, academic version. And then we have layout constraint generation, extraction, and then a placement and routing engine. Right? So essentially, as you can see, there are a lot of algorithms which have been used, including machine learning, AI, pattern matching, some deep learning. But we also have a lot of more conventional, like analytical algorithms, for example, placement, and for routing, we have used A-star search, which are pretty widely used for digital routing as well, right? So I will show you some of these details, but because there are a lot of stuff, right? So I won't be able to show a lot of technical details, but hopefully through this talk, you can get a good overall picture of Magical. And the device generation, basically, once you have the size, you have to generate the primitive, which will be later on used for placement. And Magical, we have not only this more like a component level, which can do this, for example, if it's a simple OTA or some of this, but this like building blocks for big analog circuits, right, systems. We also have a hierarchical framework. Essentially, you can do a block level synthesis, but you can also integrate them into different hierarchical level, and so that like this is a pretty advanced ADC chip. As you can see, you can do each building block level, but once you put them together, you can still have all this nice symmetry structure, etc. Right? So all right, let me now show you different components for Magical. So as I mentioned, right, so first we have this parametric device generation. So the input is the circuit netlist and the design rules. And then the output is the device GDS2 layout. And then what's its bounding box and pin location, etc. Essentially, my students, we implemented this parametric device generation kernels using Python. Actually, Minjay, he's actually in the audience. He's the one did this. And this is a correct by construction. And while we construct those device, right, primitives, for example, NMOS, PMOS with guard ring and capacitor and resistor, etc., right? They are all DRC clean and LVS clean. And again, as I mentioned, right, so there's not really too much kind of intellectual novelty here, but we have also made it open source so that if you say, hey, I want to have a tool that is not dependent on a commercial tool to generate layout, you can actually use this.
Hey, David.
Yes.
Yes, Rob. So does this require information from a process design kit typically?
Oh, yeah, of course, right? Because you need to make sure it is DRC clean.
Right. Okay.
Uh-huh.
So then that assumes then that, I guess for most folks, that would be based upon a relationship with a foundry like Samsung or TSMC and having access to their PDK, unless someone is using, for example, Skywater's open source PDK.
Yes. So yeah, this one, but we have it in different parameters, right? So while we are generating those devices, so the design, once you read the PDK, right? So then you pretty much set those parameters, then you can generate those, right? So for different design rules, PDKs, you will set different parameters. Right?
Okay. Thank you.
Thanks. So then the next big chunk is how do we do analog layout constraint generation, right? So for analog layouts, there are a lot of constraints, right? Most important constraints are so-called symmetrical constraints. Essentially, right, usually you would like, for example, this net, these two nets need to be symmetric, and this transistor and this transistor need to be symmetric, and so on and so forth, right? So, usually we mostly focused on the symmetrical constraints, right? And because originally the DARPA requirement is that, hey, your netlist is an unannotated netlist. So basically you just have a flat netlist or hierarchical netlist, but you didn't say, oh, this net and this net need to be symmetric and so on and so forth, right? You could also have an annotated netlist, and then we just read in those constraints and then write into our database, right, data structure. So basically, we have used different techniques, including small signal analysis and also using some, pattern matching, and also at the system level, we have done some design hierarchical analysis and also use some graph similarity. Again, I won't go into details, but the key thing, key takeaway is that we can extract those basically symmetric constraints for the nets, as well as for the active components, transistors, right? And you can do it in a component level, very local scale. But meanwhile, if you have big building blocks, we can also say, hey, this subcircuit and this subcircuit need to be symmetric, and so on and so forth, right? Okay, any questions here? So then basically, also I would like to mention, right, those kind of constraints, right, will be used later on during our placement and routing, right? And some of these constraints even is used if it is self-symmetric constraint, even it is used in the device generation, right? Okay. So yeah.
So that's interesting. So the requirement from DARPA was an unannotated net list. And then effectively you're deriving the constraints based upon the analysis that you do of the input data.
Yeah, based on the input, there's netlist connections, right? Stuff like that. All the signals from here. This I think maybe Minjie, you can give a little bit detail. You are interested, but essentially, right, we do those kind of analysis, then based on the signal analysis, and then some kind of pattern matching and some kind of graph analysis. Then we kind of figure out who and who. I mean, we could do more than needed, or we could miss some, right? Because hey, sure, this is but in general, right, we found we can find those, and is in particular, right, because analog circuits, they're very they prefer a lot of symmetrical structure.
Right. Okay, thank you.
Okay, thanks. Then we are going to, we have all the instance, right? We have placeable, building bounding box, and then the symmetric structure, the nets has all those structures, etc. And then we are going to do placement. So our placement, usually when you are dealing with placement, right, you have global placement and detail placement, legalization detail placement, right? So our global placement engine is based on a nonlinear programming based global placement engine. And here's the overall flow, right? So you have global placement, then you will do detail placement. Our detail placement is based on linear programming based detail placement, and you will do area based compaction, and then you will do further wire length driven compaction. In terms of the global placement, which determines the overall quality, right? but not necessarily totally legal, but we are going to have those iterations. Usually, global placement has all these iterations. It's a nonlinear, and then you are going to iterate. And while we are doing this, we also have the constraints into it. So that is if the cells say, hey, you need to be symmetric with certain axes, during the placement, we want to make sure they're more or less symmetric. And also our placement can also take into some system signal flow, right? As I think Rob, you mentioned, right? So usually when designers design analog chip, they probably know how their signal flow needs to kind of go, in maybe top down, left to right, and so on and so forth, right? So you could also have a system signal flow to guide the placement. And we found that, later on I'm going to talk about it, right? So if you use that, it actually can get better performance, right? Okay, but this part, right, maybe designer provided, right? But again, right, even when we are talking about those constraints, right? So we have automatically generated ones, but meanwhile, we can also have a designer. If designer say, hey, these two blocks need to be symmetric, so you just write it in a certain file format, and then we read it in, and then we're going to take care of it during the placement. Then, here's just some examples of how placement works, right? So at the beginning, it's not legal. You gradually spread the cells, and while you are spreading, you try to meet the symmetric constraint. As you can see, here is the center axis is then symmetric, mostly between the this left and right. And here's just an example of our bigger ATC. As you can see, it has pretty nice symmetric structure, and the placement can make it pretty compact. So while we do placement, so one thing you notice that usually, right, how do we deal with well, right? When you have standard cell, well is pretty for digital designs is pretty straightforward and is automatically taken care of, right? But for analog designs, you may also need to generate the N wells, right? Those wells. So what we have done is that we also one thing is that usually designer automatically draw it, right? But we actually also developed some machine learning algorithm based on GAN, right? Generative Adversary Network. Again, I won't go into details, but basically it will automatically generate the wells. While you generate the wells, right? We use this. Again, here, as I mentioned in the title, human intelligence, right? We have a lot of design data. I mean, this well-generated data from original designs, right? And then we will train it, and then we can automatically generate the wells. And another thing is that, of course, when we are talking about well, there's also well proximity effects, and this is just to generate the well, right? Ideally, you would also like to combine this well generation together with placement, and because by doing that, you could probably because otherwise, if you just generate a well, generate placement and do well, and then as the post-processing steps, your placement may be suboptimal, and then so ultimately you may like to have this loop, right? So actually we have some ongoing work on that, right? So another thing related with placement is like, of course, when we are doing placement, so usually, right, even for digital, right? So you mostly only consider, maybe area and wire length, right? So those are the basic objective you would like to minimize, right? But the wire length may not be enough to reflect the analog IC performance, right? Of course, wire length is still, the first order is very important, no matter whether for digital or analog, because if you have too much wire length, your parasitic will be terrible, and then delay, power, all these are bad, right? But still, right, analog has its own kind of performance metrics. So sometimes, like those, noise and other, different, CMR and offset, all kinds of metrics, right? So, if you have two layouts with similar wire lengths, but they may have very different post layout performance in terms of those, analog metrics. So, but to do those kind of simulation, it could take a lot of time. Let's say if you have two layouts, how do you know this one is better than the other, or one is not as good as the other, right? It's pretty hard to say, right? So that's why we hope to also have some placement quality prediction, let's say without running detailed post layout extraction simulation, and then you can directly get the placement quality prediction post layout. So one nice thing of our Magical is that because we can automatically generate, many different layouts, during our placement, right, we can adjust the net weight and other things, right? We can actually generate thousands or tens of thousands different layouts very fast. And then actually we have some script to, once you for generate each layout, we actually we will do layout extraction and then do simulation. Then based on the metrics, ultimate metrics, for example, CMR or offset, etc., right? So then we can kind of say, hey, this placement is good. The other one, not good, right? So essentially, we can prune out bad layout directly early on during the design, right? So if we have this kind of placement quality prediction, so we have built some CNN models for that, and we also released this UT analog layout data set with post layout simulations, right? For certain technology that TSMC that we used, right? 40 nanometer. So I think this is a pretty interesting direction in the sense that, okay, if you can automatically generate, because for manual designers, there's no way that they can explore so huge design space. But once you have this analog, usually they were based on their past experience, right? Usually, but now you can actually generate tens of thousands of different layouts, and let's see, hey, which one is better, right? So that's how we can then use this to guide our placement.
Yeah, that's pretty powerful, because I mean, in general, you're right. It's analog engineering, if you will. It's effectively kind of black magic, or in other words, you have
they have their kind of history of kind of success, some kind of, they think, oh, this is the way, they just do it this way.
Yes,
They probably want to try many different things, right?
Yes.
But with this, we can actually explore many different things. I'm not saying that they are really accurate, but I think they can filter out, and then you can do further simulations, right?
Well, that's comparable to digital design, right? Where it's often course-based metrics that are easy to calculate, that lets you filter out different things that are not as good as others.
Right, exactly, right. So and then in terms of our analog, the entire design flow, right? So we can have a hierarchical flow, and we can also, I think I already mentioned this hierarchical flow, but we can also do simulation in the loop when needed, right? Because simulation is very expensive. You don't want to do simulation, while you are running all these place and route, right? So post layout extraction, right? That's very expensive. But with this kind of prediction, you can help you to do that. But when you are very close to, the, let's say, later stage, you are converging, you may want to do real simulations and see that, hey, after you have done your place and route, whether that will really meet your performance target, right? So that's why we have this kind of options there. You can do simulation in the loop when needed, especially at the later stage. And because this simulation, it is very accurate, and also we can combine it with Bayesian optimization, and then to adjust, for example, our placement and routing knobs, right, to try to fine-tune our quality of results. Right? All right, so I think I already talked about, right? So essentially, for example, during the placement, we can then adjust the net weighting, and then you can regenerate new placement and routing. Then you can do this loop and then help portfolio. Our main reason to do this is DARPA also hopes that, hey, it's a one pass and it will be a tap out kind of quality. But if we just do some wireless, we are not sure whether that's tap out quality, right? So at the end, you probably want to have some of this in the flow, right? Okay. All right. So another thing that during the placement, as I mentioned, right, we can also add some system signal flow. For example, that the system signal flows from here to here to here to here, right? So if you have optimized the system flow, hopefully it will be more straight. Otherwise, you may have detours, and if it is irregular, signal goes north and then goes south again, right? That's not good, right? So Right. Again, this portion, right? So since it's a system level, right? Usually it can be a designer provided, right? If at the top level, the designer has some system level knowledge, and then they just provide this and in certain file format, and then we can read it. Yeah. So as I mentioned here, right? So we also, once you have this kind of system flow, our placement can consider the system flow. And we can extend the analytical placement engine to consider this. For example, we want to minimize those kind of angles, right? So, if the angle is 0, so that's like straight, right? If the angle is very big, that's not good, right? So it means you have more detour, right? So anyway, we can then add those kind of system signal flow into our nonlinear placement optimization engine. Okay. And now in terms of routing, right? So routing, our input is routing constraint and placement plus PDKs, design rules, right? And then our output needs to be a LVS and DRC cleaned GDS2 layout. So, but routing is actually quite challenging. There are actually a diverse human experience, usually, right? So especially for analog designs, they have some, there are ways to do it, right? And there's also many challenges, the routability, ping access, etc., and also design rules, right? So that's why when we are doing routing, we have published some kind of global routing for which we call genius route, which provides some routing guidance, again, based on some machine learning. This is a generative adversary network. Again, I won't show in details, but basically, right, based on some past experience, you can say, hey, it should roughly route in this kind of, regions, this way, stuff like that, right? And then you can then use this to guide the detail routing, right? But in our Magic 1.0, right, we actually had a more flat route, right? So it's directly a grid-based routing. Which can handle DRC, because our early version of Magic Router is not a grid-based routing. It's more fine grid or even gridless routing. Right? But that's pretty challenging for us to do all the DRC and especially advanced technology nodes, right? So now we are having a grid-based routing for speed and also the DRC handling. And the core engine is the A-star search, which is very popular in all the routing engines. Right? And we have DRC check, and also the routing will handle the symmetric awareness, right, in our routing. And our router also support the variable widths, and you also have multiple veer cuts, right? And when you are dealing with power and ground, we have some special handling. And we also have post-processing steps to fix DRC errors. Again, right, this is the overall routing flow. You have some pre-processing, and then you have some core routing procedure here, and then you have post-refinement to, in particular, correct the DRCs. So in the core routing, we have some ping clustering and constraint-aware connection and etc. Right? So those, this is kind of a lot of route and then some repub and reroute process. So in terms of routing constraints, right? For example, this is a mirror constraints, and then there are some self-constraints, symmetric constraints. But sometimes you may also have a cross symmetry, right? So because two nets go this way, and then sometimes it is not perfectly symmetric, but then we can do some partial symmetric. Essentially, we would like to have as much symmetry as possible, but sometimes you cannot have perfect, so we still can handle some of that. And again, right, we to handle all these electrical constraints, we may have multiple widths and so on and so forth, multiple veer cuts. Because ultimately, right, as I will show you, right, so when we develop a 1.0, so we are at that time trying to tap out a chip, right? And so ultimately, since we need to tap out this chip, right, there's a lot of like engineering details and dirty stuff we have to handle, right? Including like also IR drop, etc. So now let me show you some results. And so we have tested the Magic on many different components. So for example, like here's a comparator, and this is the manual layout, and this is our Magic layout. As you can see, these two layouts look very differently. However, if you do post-extraction simulation, I mean, Magical is still, I mean, this is the early version of Magical, by the way. So not our the latest one, but it's not as good as Manual, but it's still pretty reasonable. And but in terms of this is another more complicated one. It's a two-stage Miller compensated OTA, and my collaborator, my co-PI Nansung, and he had those tapped out before. This is a manual layout which has been tapped out in TSMC 40 nanometer, and this is our Magical layout. Again, right, the layout looks very different. And but if you do post layout extraction in terms of all these different metrics such as DC gain and phase margin, CMR, etc. So I think it's pretty comparable. And for example, of course, this offset at this time is still not as good. And offset, by the way, right, it's quite related with the symmetry. And but later on, we have our newer version actually is more powerful, right? But again, right, so here it shows the Magical can get pretty competitive results. But in terms of runtime, right, if you do this by hand, right, so it could take a week or so, right? But with our Magical, it runs in seconds. So here are just some more designs, right? So there's a schematic and the layout between Manual and the Magical. And this is another inverter-based OTA. So we have tried a different kind of circuits, right? Now let me show you actually one of the real exciting things that we had, right? So we actually, for this Magical 1.0, we actually tried it for a pretty complicated and high performance, ADC design. It's a 1 giga sampling per second, a third order high performance, the continuous time delta sigma modulator. So here is the schematic. As you can see, it has variable sub-blocks, including 3 integrators and 1 passive and 2 active, and also have 2 FIR-based feedback DACs, and then comparators, and also a bunch of digital logics, right? Blue logics. And so this is the entire, actually packaged. As you can see, here's our ADC core. It has some peripheral circuits to help to do the testing, right? And this core area is about 22,000 square micron. And the chip is about 800 micron by, this entire chip is 800 by 550 micron. So as you can see, we tapped it out at the TSMC 40 nanometer, right? Thanks to TSMC, yeah. So actually we have a shuttle, free shuttle at UT Austin, and that's why we can actually have, we can tap it out. And then here's the PCB board, and here's a chip micrograph of this synthesized ADC. Okay, here's basically the ADC part, and these are some peripherals, and here's the wire bonding. And we have actually got a bunch of chips back. And so here, as you can see, it's 8 different chips which have been packaged and measured. And this is one of the representative chip measurement. So as you can see, the bandwidth is 5 megahertz, and this one is 500 kilohertz. And the SFDR and SNDR are all pretty competitive. And we also run for different chips. As you can see, they are actually pretty consistently in the range between 78 and 81, 82. And this is the SNDR, again, right? It's pretty consistent. And the design margin is also actually pretty good. So we can also compare it with other state-of-the-art continuous time delta sigma ADCs. And so actually among these, right, so this, okay, let me actually use a pen. So this one is actually the previous chip that has been tapped out. Basically, our design is the same as this design. It's just like this one, our layout is 100% automatic, and this one is 100. This one is manual layout, right? It's 100% manual, and this is 100% magical. And we also have, I mean, of course, before this is actually a pretty high performance design. It was published in IEEE Solid State Circuit Letter. It's a very good journal. And so at that time, it also compared with some other, continuous time delta sigma. That's actually pretty good performance. So then we compared the automatic layout versus this manual layout. As you can see, actually, the overall floor plan looks pretty similar, right? One thing I have to say that we actually, the only thing manual constraint we add is a signal constraint. We added the signal flow, and then the rest is basically automatic placement and routing. And and in terms of the overall performance and so on and so forth, right? As you can see, they are really close. Like as you can see, the area is very close, and also the power, actually, in terms of power, ours is even slightly less. The bandwidth and frequency, they are all the same. And then if you look at the SFDR and SNDR, I mean, their SFDR is slightly better, but our SNDR is better. And in terms of the how many watts per operation, actually we are slightly better. So anyway, it's fairly comparable, I would say. And it's published it was presented and published in the CICC, which happened just last month. Oh, well, actually maybe 1.5, a little more than a month ago. Right? So let me actually show you some demo. Basically, so basically, as you can see, this is our file structure. And as you can see, these are our top level kind of design. It's just, right, it has, this, as you can see, it's a net list. It's a hierarchical design. And it has different, this is a SPICE net list, right? And then this is our run script, right? So basically, we're just run a top level script. And then if we run it, right, so we will read the design, generate the, all the building block, then we'll do placement and routing and generate constraints. And so actually, let me see, right. So now it's during the doing the routing, right? The routing takes more time. So which is expected because you have to follow all the design rules and so on and so forth. So it is doing all this routing. Now it's already writing routing, as you can see. The routing already, as I'm talking, right? So it's already done. So and this is the final layout. So the entire thing takes, I think, less than a minute, right? Okay, so here's our core, basically. Oops, sorry. Go to the next slide. Oh. Okay, sorry. So, all right, let me conclude. So in this talk, I kind of show you Magical, which is the open source analog layout design tools that can do fully automatic analog layout. But it can also take designer inputs if you give us the constraints. So the key components, including device generation, automatic, but in terms of intellectual part, mostly, how do we do automatic constraint generation? How do we do placement, and then how do we do the routing? But we also provided the device generation script so that you can also to make it more open source, and it has been silicon proven using a tape out. It's actually pretty high performance ADC, and we have already made the open source available under BSD3 license, so it's permissive license. And we also have released, besides this Magic 1.0 open source code, for the for the layout systems, we also released some analog layout circuit, right? Which we stripped the PDKs because there's some proprietary information there. But we also released the circuits there, as well as some data set which can help to do machine learning, right? So essentially, because Magical can generate thousands of tens of thousands of layouts very quickly, so as long as you can afford to do some simulations, then we basically just dump those into and we run automatic script to do post layout extraction and simulation. Then we can kind of do the label, right? Once we label whether this placement is good or not good, etc., then we can actually do this kind of we can then do learning, right? I think there's definitely a lot of room for to grow this kind of data sets, right? Not just for what we have, but to grow this. All right, so these are the Magical related publications, and so we started, as you can see, ISPD 2019, and now most recently we have some CICC and also a new deck paper to be presented. So, all right, with that, I would like to also thank my team. So yeah, they are very awesome, and my Magical team. So including some 3 current PhD students, Mingjie, he's in the audience. Karen and Hao, they cannot attend now, but currently actually they are interning at the NVIDIA, right? So we are trying to also extend the Magical to the future FinFET type of technologies, right? And also my postdoc, Xi Yuan, he's an analog designer, and of course my co-PI, Nansung, and so he's also analog designer. So this is actually a really nice collaboration between my background is more EDA, right, and machine learning, etc., to a really hardcore analog designer. So also like Shaolan is a former postdoc, and he's now an assistant professor at Georgia Tech, and also 2 other, like another postdoc and my former students that have been heavily involved, right? So without them, this is impossible, but I think we are very happy about what we have got so far, and we want to continue to push Magical toward more functionality and support more different kind of circuits, and also different technologies, right? But I have a relatively small team, so we can only do what what we can be realistically be able to do. Right? Okay, with that, I think I like to close and conclude, and thanks everyone. Yeah, I'll be more than happy to take any questions. If you are interested to see a real demo, I guess Mingjie maybe help. Mingjie is in the audience.
Thank you so much, David. Do you want to do a real demo now? I see that Professor Kong has a couple of questions in the chat. I don't know if you want to take those first, or
no, they can be skipped. I think they're mostly not for David anyway.
Okay.
But I just
Don't worry. Those are good questions, though.
Yeah, we will. Go ahead.
Yeah, hello. Mirjana Videnovic-Mišić from Silicon Austria Labs. Professor Pan, thank you for your presentation. It was very interesting. So I have a couple of questions, and they are mostly, let's say, related to machine learning algorithms that you kind of used. I can see that you're working, like all the examples that you presented are in 40 nanometer TSMC technology. So my question goes into direction, because you heavily rely on AI and machine learning. What is basically technology portability? How much overhead do you expect? That is first question. The second question is, let's say Align and Magical and BAG have the same, same idea regarding the fundamental blocks, which is like these device generators, but then they diverge in the way how they handle floor planning and routing. So do you see that there is a way, because all these projects are part of this initiative, that in the future there will be some standardization so such that there will be some, let's say, a convergence point where these three frameworks, which are open source, could kind of be, good practices could be used from one framework to another. Thank you.
Oh, yeah, I think this is a great question. I think you have several questions here. Right? Let me try to answer them one by one. So the first question is regarding the machine learning, right? So sure, we used some training data, and some of this is based on TSMC 40 nanometer. Of course, if you have a new technology, right? So probably you have to retrain it, but there are also techniques, so-called transfer learning, right? Actually, my group, we have done quite a bit of that, for example, for lithography related, right? So to transfer, if you train some technology from the one technology, right, you can transfer the bulk of the model, but still with some limited new learning data, you can kind of train from the current model to migrate to a new technology, right? So
I'm sorry, can I interrupt you here? I'm sorry for being so rude. So the open source data sets that you provide, I forgot the name of it, that is for, let's say, 40 nanometer technology. Is it possible to use those data sets and algorithms and then, following your procedure, like to retrain and do the transfer for another technology node? I'm asking because, we are interested also to kind of repeat, learn from you, but we need to know what are the possibilities with the things that you share. Thank you.
Well, actually, my student Minjie is here. Right? He's the one really implemented this. Maybe I ask Minjie, can you take this question? How transferable is your model?
Yeah, sure. So
by the way, if you don't mind, can you turn on your camera, right? So,
yeah.
Oh, thanks.
Hi everyone. Yeah, I'm Minji Liu, and I'm one of the Magical team members. So in terms of answering that question, if you have Magical installed, and so I think there's like two parts of your question. Is one is if the model could be transferred, and the second is if the whole framework could be transferred. So in terms of the first one, I think it would be sort of difficult. So if like that specific model would be directly transferable to another technology without any retraining, that would be hard. So you need to have some sort of data to retrain your model. But on top of that, I think the framework could be transferred. So if you can, let's say you have another technology, probably like 65 or even 28, and you transfer the entire framework like Magical with the placement and routing into that new framework, you can entirely just generate a whole new data set on your new technology, and that still would work, right? So it's not dependent on the technology node if you can transfer the entire framework of Magical to another technology node. But again, if you're saying that I have something that's working on 40, can I do that in 22? I still think that could be done with transfer learning, but it would be more difficult than transferring the entire framework into another technology and working from that.
Mm-hmm. Okay, thank you.
Okay, so Miyana, so this regarding your question of like other open source like analog layout systems, right? Back and Align and Magical, right? So Align and Magical, I think we have some similar principle in the sense that we are doing automatically generated. Both of us actually we are supported by the IDEA program. But I think there's a little bit difference in the sense that the Align are more, how do I say, they focus on more regularity structure, and we are now, I think they are more in the FinFET type of technology, and we are more bulk, and so we can do very fully kind of unstructured like analog layouts, right? But I think we share some principle of thinking in terms of how do we do automatic layout constraint generation and then automatic placement and routing. So in that sense, right? So we do share some commonality, but we are I think that the main focus is like currently we have been targeting more bulk technology. I mean, for example, TSMC, right? We don't have access of the global, and they are mostly focusing on global, right? Like those FinFET technology. Right? But in terms of bag, right? I think bag is basically they're building. Well, I think it's not fully automatic, right? It's like you have to write a software to generate the layout, right? Essentially, so I think ultimately, right? So I think how do I say it, right? So analog is such a challenging problems, right? So people haven't been, haven't been able to, they are mostly even draw layouts, right? That's terrible, right? Writing software like a bag is already, a big step to help that. But what magical and align is really, you give us netlist and we just, automatically generate the final layout, right? Without, even writing, those bag related to scripting, right? Stuff like that. So yeah, but ultimately, right, I think we'll see more converging as time goes, as all these tools become more mature, right, and being used by different, designs and also different technologies.
I think one of the challenges relative to convergence of technologies, as I've shared a bit with Tom Spiro, who works with Andrew, but certainly I've seen this within companies as well. And Michelle Lautis is on the call, who I worked with at Sun, Oracle, and Synopsys a bit too, right? Is, if from a perspective of establishing a framework where different components can be defined with an API that's well governed, that would enable innovation within the API layer that would then allow researchers to contribute to that. But as you know, we have different frameworks that are created, right? And then, which, I understand is easier, but having an established framework, if you will, would make that easier for others to plug into. Anyway, thank you.
Yeah, and this is Thomas from Infineon. So first, David, thanks for this great presentation. Very, very interesting. I can also agree to what Rob just said, that I think this is a stepwise approach. What we are currently trying to do internally in our company is more maybe thinking in this back direction first, because that's not fully automated yet, but you have the first challenge that you have to train your analog designers more programming and this kind of stuff. And then I can imagine that the next step will be then definitely this request to do more automatic stuff. And then you're also right, then probably some companies will come and say, yeah, we need more automation for bulk technologies, and others will come, we need more analog automation for FinFETs. And then I think all of three solutions, bag, align, magical, or then in some years, maybe they're called it a different way, then will have their the reason to exist. And even then to interlink with each other. And yeah, if you then also have some framework here, you can plug things in and out and so on. I can imagine that such a setup with a lot of ideas coming from universities, changing then small parts of this bigger framework could be also very interesting then for companies, yeah, like ours. But
Thank
really
you.
Great work, David. Really, really, really impressive.
Thank you very much, Thomas. Yeah, I think your comment is really well taken, right? I think that, yeah, at this stage, right, I think they are all growing, right? So we're at a certain point, right? So we'll see how to kind of, the nice thing is that they are all open source, right? So that's really nice. So
yeah, that's one advantage, probably. I mean, this is also how I understand it, why we are now sitting together.
Right.
Yeah. And of course, I mean, this putting them together, of course, is not really academic attractive. Right. Yeah, that's the disadvantage. But I think, I mean, if we are smart enough here and creative, maybe with small effort, we can bring them together, and then it's maybe getting attractive again for academic guys as well, because then you can plug and change only parts of it. You don't need to reinvent a complete framework here again. So you reuse then maybe magical, but you have a great idea at another university to change, I don't know, the router or some machine learning thing there. And then I can imagine that even such an effort to streamline it a little bit or to bring it together could then also pay off from an academic point of view again.
Yeah, totally agree.
That's a good. So David, I would appreciate the fact that the work can generate different scenario types of layouts very quickly and pick the best one. I'm just curious, has anyone yet in practice used this framework for to aid designers, if you will? So, you know, you certainly shared very good results that that's being generated by Magical, but I'm wondering if folks would possibly use that as a point to maybe just tune it slightly, you know, to get it to where they totally want it to be. In other words, the automation is acting as an accelerator in the overall design process.
So I'm not sure about, so you are talking about whether some companies has used this.
Yeah, I'm just curious, right? Because I'm just thinking in terms of industrial application where, you know, the automation gets you to, let's say, 98% of what your design goal is, and then you manually tune it. A layout designer manually tunes it just for that last little bit. That's what I'm just curious if anyone has tried this yet.
Well, I haven't, you know, because this is, you know, industry people, we made it open source, and some, you know, we do have people talk to us, right?
Right.
You know, but they probably won't tell us the details, how much they have been using it or stuff like that, right?
I appreciate that. Okay, sorry for the question.
Yeah, that's why, you know, but I think the thing is that, you know, we have made it open source and this framework, right? So anyone can use it, and it's permissible. So that means, you know, once they use it, they don't have to tell us. So
that's right. Okay.
Yeah.
Sorry for the question.
Yeah. But we have been talking to many different companies, right?
No, it's very good work. Thank you.
Thanks.
Are there other questions from the audience? Okay, if not, thank you, David and team. I appreciate the presentation today. I thought it was excellent work, and the presentation was very good as well.
All right, thanks, Rob. Thanks, everyone.
Yeah, thanks.
Appreciate
David.
your comments.
Thank you.
Thanks. Bye.
Okay, so I have updated the notes from the meeting, which I'll just resend out to folks to see it. And I do want to work on the agenda for next time, so I will do that. Some of the topics I have here is creating a soft roadmap, also looking at an open source IP catalog, and then also talking about methodology sharing and best practices. In terms of the next presentation, perhaps we could have an update from Berkeley on Chipyard and BAG. That might be the next academic presentation. So I will circle back on that. So any questions or comments?
Rob, I think the comments of Andrew, let's say these questions that he posted there in the chat, I think they are also available to not to be forgotten. Then maybe you put them also into your list.
I copied them into the minutes from the meeting. Yes. No,
Good.
I think those are very good questions.
Yes, exactly. Yeah, they're really interesting questions. I mean, for us as a potential, let's say, working group for some time. Yeah.
Yeah. No, I totally agree with that. Yeah, and thank you for calling me on that.
Thank you.
So I'll summarize these, and then we can formulate next steps for the meeting and do that online until we set up the meeting, which I hope to do in 2 weeks. Any other questions or comments from folks today?
No, thanks, Rob.
All right. Thank you, everyone. I appreciate it. And thank you again, David and team.
Thanks,
Thank
Rob.
you.
Thanks, everyone.
Yep. Bye-bye.
Bye.
Bye.